Okay? It likes polar protic because protic solvents, solvents that can do hydrogen bonding, are good at surrounding carbocations and stabilizing them. That's called solvation. They're good at solvating carbocation. Okay? So protic solvents help that. Yeah. The details, it does inversion. Inversion. This doesn't matter for our purposes, but just so you get a complete story. And retention of configuration. What that means is, say the leaving group, yeah, I should have made it like this. Say the leaving group's pointing at you guys, and this methyl group is pointing into the back room. Okay? I've decided to change this. I'm sorry. I'm not going to go into why I've decided to change that. Because you get this flat carbocation, it can get retention, which would be coming from inside the room. So the leaving group, the nucleophiles got the same orientation that the leaving group did. That's retention. Or it can come from the hallway because it's flat, come from the hallway, and then the nucleophile will be pointing back. And that's inversion, just like what we saw with SN2. Okay? All right. So, let's talk about what we're doing today. You're going to have a partner, but again, it's just like cyclohexanes. You're going to have just a data partner. That's the only reason you need a partner, because there's going to be two different reagents. And one's going to do one, one's going to do the other, just like last time. Okay. Have a data partner, so choose a partner. One chooses the starting material 1-butanol. Okay. One chooses 2-butanol. Okay. And everyone does 2-methyl 2-propanol. So everybody's doing two reactions today. This one, these two take a long time to cook. Okay. This one is, almost as fast as you can do it, as fast as you can shake it together. So while these guys are cooking, you do this reaction. Okay. All right. Okay, so let's take a look at these reactions real quick. 1-butanol. Bromide, chloride, 50 mix, okay, and sulfuric acid. Okay. You're going to get a mixture because you've got a mixture of nucleophiles. Okay. The first step in the mechanism, by the way, this is sulfuric. This is a junk leaving group, but the sulfuric acid protonates it. And then it's just water tethered onto this carbon, okay? And so then it becomes a great, just like what we saw with cyclohexanes. All right. According to what I've taught you, which one of the two mechanisms would you expect this reaction to go through? You can totally answer that if you're wondering, like, come on, that's a hard, it's actually not quite that hard. I mean, it's extra hard for you guys because this is brand new. Still, not an unreasonable question to ask. Any idea which one you think would be favorite? What's that?
The chloride. Never mind. The chloride.
No.
The bromide.
Well, you're a step ahead of me. Hold on to that answer. Let's first decide which reaction, SN1 or SN2.
Oh.
Okay, sure which?
SN1.
SN1, close.
SN2.
SN2. You were just, yeah. All you? Do you have me next semester? I'll keep doing that. I'm tired of it. Okay, so does anybody see, this is SN2. That's what we'd expect. And the whole purpose of these 2 weeks is to prove it. All right? But why was I expecting, perhaps even though it's 5 minutes old in your brains, why was I expecting that you might know that? What could you look at this and go, oh yeah, that's going to be SN. That's going to be SN2. Look at this little line here. It don't happen. SN1 doesn't happen with a primary substrate. And once this gets its extra proton and stuff, that leaving group is a primary leaving group. Okay? Does that make sense? I don't remember if I said why primary doesn't happen. It doesn't happen because a carbocation is just too unstable. Okay? It doesn't have enough carbons to help out. And all that extra carbons helping out in the tertiary is why it's so good. Okay? So we would expect SN2. Okay? All right. What? Mac? X Mac? Okay. SN2. I've got the wrong thing in my notes. I'm already taking this class. SN2. Now, what evidence? I forgot to write it here, but next week, what we're going to do is we're going to see what this ratio is. We're either going to use NMR or we're going to use GC, okay, like we did for several weeks. What? So we'll determine this ratio. And I'll talk about a little bit more about how next week. But what evidence from ratio could prove that? Okay? That's vague. That might be too hard of a question to ask when this chemistry is so good. But Kira?
There's more of the chloride.
This close.
There's more of the bromide.
Yes!
Oh, yeah.
We would expect more bromide. Why would we expect more bromide?
SN2 likes better groups? Oh no, that's SN1. Because bromide is more polarized.
Because what?
It's more polarized.
It's more polarizable, exactly. So it's a better nucleophile. And SN2 cares. SN1 don't care. Okay? SN2 is gonna react with anything that it runs into. Okay? So if it really is an SN2 reaction, we can expect more of this kind because the bromide is better nucleophile than the chloride. Okay? All right. Awesome. Okay. Is this annoying when teachers show like erase parts and then, oh, it's not? Oh, okay. I know that was super annoying maybe. It's much faster for everybody. Did I ever tell you guys I had a physics teacher when I was an undergrad who had an eraser and a chalk in one hand and would go, you know what I mean? Right?
Dude.
Physics.
For real?
Yeah.
Mark
Yeah.
the-
He's totally insane.
Oh my god.
Sweetest guy ever. Totally insane.
I've had another teacher say that they had a teacher do that SN2.
The Martin.
I think it was Martin.
Oh my god.
2 methyl, 2 propane. Okay. I think maybe in the worksheet, I don't even use this name. I can't remember. I think I may just call it. It's a totally perfectly good name. T-butanol. Okay. You guys probably haven't named alcohols yet in class. But those are, you know what a T-butyl group is, right? Oh, you know what I know he's talking about a T-butyl group is. That's a T-butyl group, right?
Yeah, sure. Totally.
It is now. Oh, tertiary.
What?
Is that right?
Did you name
It
alkanes?
makes it
You
sound.
gotta name alkanes, right? Isopropyl?
Yeah.
Okay, I saw the nods. There's the ETOP. It's in the notes. It's anyway, it doesn't matter. Okay, sorry.
Okay.
2 ways you can name alcohols. One that fits and that fits, but that's a heck of a lot easier. Oh yeah, here he is. That's why I didn't need it. Okay. What mechanism do we expect?
SN1.
SN1. Very good. Okay, we're getting the dance here.
Oh, I was just
SN1.
taking
All right. What evidence, if that's indeed the case, what evidence, we'll use GC for this one, we'll get the ratio, talk about how we do that.
It's 3 prime.
What's that?
It's the 3rd primary.
Yes, that's how you knew to make this guess. Next question.
Totally.
What evidence from the ratio could you point to prove that hypothesis?
Should have
Equal ratio.
What's that?
It's an equal ratio.
Bingo. Equal ratio, because who's better nuke? Who's the worst nuke? Don't matter. Okay? It's whatever the carbocation runs into. So if we start with 50-50, we ought to get, and yeah, I really need to add this caveat. We ought to get around 50-50. Okay? I'm giving you the idealized theory. In theory, there's some variations. Or in practice, there's some variations to this. Make sense? All right. This being so new to you guys, this is so this is now so that is 2 okay. What the heck is this? Sorry, something this would be too hard to ask you to guess. I mean, because that's, what type of is that? Tertiary, primary, secondary?
Secondary.
It's secondary, yeah. And secondary, if you look back at your chart, secondary, both can do secondary. Okay? So now it's starting to get more subtle. Okay? And so, it's hard to say. If somebody had asked me a prediction, okay, I might be tempted to go, well, let's look at the solvent. The solvent's a good, and that's what, if this is an exam situation, not necessarily our lab situation, this is an exam situation, and you got a secondary substrate, and you're not sure, is this going to go SN2 or SN1? Go to the nucleophile. Polar A product, SN2. Polar product, SN1 most likely. Here, hard to say. Okay? So, SN1. But if it's SN1, okay, we ought to get a ratio, again, that's what, Joe? Joe?
Equal.
It's equal if it's SN1, okay? If it's SN2, really, you kind of expect to get what, we don't know what that ratio is going to be for the SN2 one, the primary one, okay? But once we get that info, we ought to expect this ratio to be similar, okay? If bromide's really important, if this is strictly an SN2 reaction, okay? Then the ratio here should be similar to what we saw with 1 butanol, okay? All right? The thing that I'll throw out there is sometimes some reactions can go through both modalities. They can do it both ways. can be nucleophile comes and kicks the leaving group off, or the leaving group just takes off, and then the nucleophile comes in. Okay, it's not impossible. We teach it as two sort of dichotomy situations, yeah, but it is actually possible to do both. And you'll just have to see. You'll have to see which ratio does this guy for the TVU. Which ratio, product ratio? You know what the product is, right? Chloride, bromide. Which ratio does this resemble of the previous two reactions? Okay, or maybe it's a mix. We'll have to see. Does that make sense, guys? Okay. Yeah. Okay. I was going to talk a little bit about the workup and everything like that. I don't think I'm going to do that. I think I'm going to make some pictures while you guys are cooking because I want to get you guys going. I spent way longer doing this than I had anticipated. Okay. Do you guys have any questions for me? Get a partner, pick which alcohol you want to do. This is kind of nice because this is one time we're doing it basically identical. The one thing I would say, guys, sorry, the one thing I'd like to try instead of exactly how it says it, don't use 0.75 mLs of the t-butanol of the alcohol. Use 1 ml. Okay? You were going to use 0.75 of a ml, use 1 ml. Okay, so we make sure we get product again.
So, just to confirm, while it's heating, we're gonna go to the second part that it tells us to. Okay.